Hey everyone, and welcome back to the channel. Today, we're re-diving deep into the heart of our solar system to talk about something that affects us all, yet remains one of the biggest mysteries in modern science: the sun's magnetic cycle. You've probably heard that the sun goes through a cycle that lasts about 11 years. This isn't just some random number, it's the time it takes for the sun's magnetic poles, its north and south, to completely flip. Imagine Earth's North Pole becoming the South Pole, and vice versa. The sun does this like clockwork, every decade or so. During this cycle, the sun's activity, like sunspots, solar flares, and massive eruptions called coronal mass ejections, goes from a quiet minimum to a chaotic maximum, and then back again. This whole process is known as the solar cycle, and it's driven by the sun's incredibly complex and powerful magnetic field. But here's the thing: while we know that it happens, we don't fully understand why it happens the way it does. Let's start with what we do know. The sun isn't a solid ball of rock like Earth. It's a giant sphere of superhot, electrically charged gas called plasma, and it doesn't rotate like a solid body. The sun's equator spins much faster, taking about 25 days to complete one rotation, while its poles lag behind, taking around 35 days. This difference in rotation speed is called differential rotation, and it's the key to everything. Think of the sun's magnetic field lines as rubber bands stretching from its north pole to its south pole. As the equator spins faster, it drags these magnetic lines along with it, twisting and stretching them around the sun's midsection like spaghetti wrapped around a fork. Over time, these lines get so tangled and wound up that they become unstable. They start to poke through the sun's surface, creating cooler, darker areas that we see as sunspots. These sunspots are regions of intense magnetic activity, and they are the launch pads for solar flares and coronal mass ejections. Eventually, the magnetic field becomes so complex and tangled that it essentially collapses and reorganizes itself. But with the polarity flipped, the old South Pole becomes the new North Pole, and the cycle begins all over again. This whole process of twisting, tangling, and flipping is called the solar dynamo. It's a beautiful theory, and it explains the basic 11-year cycle pretty well. But when we look closer, the beautiful theory starts to show some cracks. Big, gaping cracks. In fact, one of the most baffling questions is, why isn't every solar cycle the same? If it's a predictable process of winding and unwinding, you'd expect each cycle's peak to be roughly as strong as the last. But that's not what we see. Some cycles are incredibly intense, with thousands of sunspots and a constant barrage of solar storms. Others are surprisingly weak, almost disappointingly quiet. We have historical records of sunspot counts going back centuries, and they show this dramatic variation in strength. Why does the sun's magnetic dynamo sometimes produce a powerhouse of a cycle, and other times, it seems to barely wake up? The difference is huge. A strong cycle can have a major impact on Earth's technology, while a weak one might pass by almost unnoticed. What's the hidden variable that controls the volume knob of the solar cycle? We simply don't know. It gets even stranger. Sometimes the cycle seems to almost disappear entirely. Between the years 1645 and 1715, astronomers observed almost no sunspots at all. This period is now famously known as the Mondor minimum. For 70 years, the sun was eerily quiet. It's as if the dynamo mechanism nearly shut down. This wasn't just a slightly weaker cycle, it was a fundamental change in the sun's behavior. And fascinatingly, this period coincided with a phase of the Little Ice Age in the northern hemisphere, suggesting a link between the sun's magnetic activity and Earth's climate. So, what happened inside the sun to cause the Mondor minimum? Did the dynamo forget how to work? Did some internal flow pattern change, preventing the magnetic field from amplifying? Scientists have proposed various theories, but none can fully explain this prolonged solar slumber. It's a stark reminder that we're missing a fundamental piece of the puzzle. On the complete opposite end of the spectrum, the sun can also go into overdrive and produce what we call super flares or super solar storms. These are events that are hundreds or even thousands of times more powerful than anything we've observed in the modern era of satellite monitoring. The most famous example is the Carrington event of 1859. A colossal solar storm slammed into Earth, so powerful that it caused telegraph systems, the high-tech of the day, to spark, catch fire, and even operate with their batteries disconnected. Auroras, the northern and southern lights, were seen all the way down in the Caribbean and Mexico. People in the Rocky Mountains woke up in the middle of the night, thinking it was dawn because the sky was so bright. If an event of that magnitude were to happen today, the consequences would be catastrophic. It could cripple our power grids, fry our satellites, and knock out global communications for weeks, months, or even years. The estimated cost could run into the trillions of dollars. And here's the scary part. By studying tree rings and ice cores, scientists have found evidence that Carrington-level events might happen every few hundred years. This means the sun is fully capable of unleashing this kind of fury, but we have no way of predicting what conditions inside the sun lead to these extreme once-in-a-century storms. Why do they happen during some solar cycles and not others? Is it just a random statistical fluke, or is there a specific mechanism that gets triggered? Again, the answer is, we don't know. The core of the problem lies deep beneath the sun's visible surface. All this magnetic drama is generated in a region we can't directly see. The solar dynamo is thought to operate primarily at the interface between the sun's radiative zone, where energy is transported by photons, and its outer convective zone, where hot plasma bubbles up to the surface like in a pot of boiling water. This boundary layer, called the Tachocline, is a region of immense shear, where the fast, rigid rotation of the inner radiative zone meets the churning, chaotic motion of the convective zone. This is the engine room of the solar cycle, but it's located about 200,000 kilometers below the surface. We can't send a probe there. All our information comes from indirect methods, like helioseismology, which studies how sound waves travel through the sun, kind of like a solar ultrasound. These methods give us a blurry, indirect picture, but they don't give us the fine details of the plasma flows and magnetic fields that are crucial for making accurate predictions. It's like trying to understand how a car engine works just by listening to it from the outside. You can get the general idea, but you'll miss all the intricate details of the pistons, valves, and spark plugs. So, why does this all matter? Understanding the sun's magnetic cycle isn't just an academic exercise, it's about protecting our modern way of life. We live in a technological civilization that is increasingly vulnerable to the whims of our star. From GPS navigation and communication satellites to our planet's power grids, the infrastructure that underpins our society is at risk from severe space weather. Without a better understanding of the solar dynamo, our ability to forecast these events is limited. We can see a solar flare after it has erupted and give a few hours or days of warning if a coronal mass ejection is heading our way. But we can't predict the overall strength of an upcoming solar cycle or the likelihood of a catastrophic superstorm. It's the difference between predicting tomorrow's rain and predicting if next year will be a drought. Scientists around the world are working tirelessly to solve this mystery. New solar telescopes, like the Daniel K. Inouye Solar Telescope in Hawaii, are giving us unprecedentedly clear views of the sun's surface. Powerful supercomputers are running increasingly complex simulations of the solar interior, trying to replicate the dynamo in a virtual laboratory. Every new piece of data, every refined model, brings us a tiny step closer. But for now, the heart of our sun keeps its deepest secrets, reminding us that even the most familiar object in our sky is still a profound and powerful enigma. Thanks so much for watching. If you're fascinated by the mysteries of our universe, make sure to hit that like button and subscribe for more deep dives into science and space. And let me know in the comments, what do you think is the biggest secret the sun is still hiding? See you in the next video.